Hello and welcome. So in this video, we will take a look at the current control system. So the entire FOC system is implemented inside this subsystem. So this is responsible for taking the reference current, ID and IQ and generating the gate pulses for the inverter, which will try to achieve the set speed or set by the user. So not only it does that, since it is a sensorless FOC system, it also estimates inside the subsystem. There is a flux estimator, the position estimator, slip speed estimator. All that estimator is inside this current control subsystem. So in the last video, we saw about the speed control system on how it generates the ID and IQ reference current given the desired speed by the user. So we will give the desired speed, for example, say 1480 RPM. So it will generate ID and IQ reference current taking into consideration all the motor's current state and motor's parameters, and it will try to produce the ID and IQ reference current to achieve that set speed by the user. So now we take a look at the current control subsystem. So this current control subsystem is like it is an interrupt service routine. So it will be run only when there is an interrupt. So that interrupt is generated by the PWM timer. So I will explain. So this is a PWM timer. So inside the C2000 there is a module called EPWM, or enhanced pulse width modulation, which will generate this up and down triangular wave. So this is a counter which keeps on incrementing, goes to a specific value, then counts down, counts up, counts down. So this EPWM module will trigger the start of conversion for the ADC. So we are using ADC to measure the motor currents, the A phase and B phase. We are measuring the two phase currents. So this PWM timer will trigger the start of the PWM timer will trigger the ADC conversion, ADC start of conversion. So the ADC will sample, and it will, since it is a successive approximation type ADC, so it needs some finite time to convert the analog value to the digital value. So in this you can see it takes some finite time to do that. After that, the ADC converts the motor currents to the digital value. It then triggers the ADC ISR. ADC, analog to digital converter. ISR stands for interrupt service routine. So the ADC gives one interrupt. So the interrupt, after that interrupt has been generated, there is a subsequent function that has been run, that is called interrupt service routine. Routine is something, nothing but a block of code which will run after the interrupt has been generated. So this ADC interrupt service routine is our current control subsystem. So the ADC, that system will run. So this image is from microchip. This if you click on this, it will open a PDF. So you can read that PDF. So you can see there is this function. The inputs to the block are from the speed control system, and output are the gate pulses of the duty cycle, which goes to the inverter. And you can see this ADC interrupt. This is the trigger which makes this function run. So I will show how to create this particular block, this type of block in MATLAB. Open the sensorless FOC. If you type on this examples, sensorless, it will sensorless FOC of induction motor. Okay. Now let's create a new model just to show how to create this type of trigger. This is called a triggered function. So the function can be triggered by any event. So for example, here it is triggered by an ADC end of conversion. So after the ADC has finished converting the analog motor currents to digital value, it will post an interrupt. Then following that interrupt, we will run this function, or the subsystem in this case. So let's create a new blank model. For example, let's add some, this is some dummy system just to show you how to create a function triggered subsystem. Let's connect a scope to it. For example, you have made some system like this. You want to make this triggered subsystem. So you have to select this, and then in the after you select, there is one this three menu icon. So if you hover over this, there is create a function called subsystem. So if you click on that, so you can see it has created a subsystem. So all the blocks within the selected region is inside the subsystem, and there is one port at the top. This is called the trigger port. So we can trigger from any event. So for example, I'm triggering from a constant. This means nothing but in your actual code you can trigger the system with any event of your liking. So if you double tap on that, you can see there is a port 1 and port 2 similar to any subsystem. There is incoming port and the blocks inside this and outgoing port. And you can see this special block has been added by the MATLAB when we created that function triggered subsystem. You can rename it like ADC event ISR, something like that. So if you go back and see, if I expand this, you can see ADC event ISR. So this is an equivalent to program in programming a function. It is equivalent to this subsystem. So it is triggered by this event. It can be anything. If you, for example, if you receive any data from the serial communication, you need to update the global variable. For example, in our system, we update the speed reference whenever the host or the user changes the speed reference. We will receive it through the serial communication. Once the serial communication is received, we will we will run a particular system which will update the global variables which contain the speed reference variable. So you can do things like that. So this is how to create a function triggered subsystem. Okay, so this is how we created an interrupt service routine. Okay, now let's go into this current control. So last time we looked at all these blocks. Now let's go into the current control system. So in that you can see there is from the input port, there is some input port 2, the feedback sim. So this as I said in my overview first video, this entire MATLAB simulation can be run in two modes. Code generation mode, that is if you want to deploy it to the hardware, you can connect this launchpad TIF28379D, this launchpad through USB. Then you can convert this entire simulating model into C code and dump it into the C2000 hardware, the launchpad, or you can simulate it entirely in this virtual environment, virtual MATLAB environment. So when we are simulating virtually, it is called simulation mode. When we are dumping into the hardware, it is called code generation mode. So because we are generating code to run on the C2000 hardware. So here the feedback sim. So if we are running in actual hardware, we will sample the motor currents from the terminals through some op amp or some circuit, then give it to the ADC of C2000. But if you are running in entirely simulation mode, there is no processor here. There is no C2000 processor here. The entire thing is running on the MATLAB or host computer laptop. So we need to give the motor reading. So you can see inside this, we will take a look at in a later video. Inside this there is a model of an induction motor. From that, two motor currents are being sampled and given to this flag. This is a flag which will virtually connect these two. So instead of connecting directly through wire, they are used they have been used some flags. So we are just giving the motor currents from the simulation virtual motor to this virtual current control system. So in hardware we don't need that. In hardware, actual ADC, we will take a look. So this is the hardware driver blocks. So this blue box is nothing but just to separate, visually separate, you can create it like, if you want to select these two and create an area. So if you want to create an area, then you can current control. So you can change the colors, and this is just to visually organize the your simulation. This hardware input block, if you see, there is this icon, a two stacked squares icon. So this means there is a two subsystem which will run conditionally, one in simulation mode and one in code generation mode. The code generation mode is grayed out because currently it is defaulting to the simulation mode, but there is also a code generation mode. In this, if you go into, okay, these two are hardware specific blocks and which are available in the C2000 microcontroller block set. And since our launchpad, this example is based on F2837XD. XD means there is different versions, 8D, 9D. So our version is 9D. So we can use this general software. So this block, ADC block, you can drag it and drop. So this ADC block, we are reading two motor currents, right? Phase A and phase B. So if you double click on that, so in the C2000, this launchpad, there is three ADC modules. You can click on that. Sorry, four ADC modules, A, B, C, and D. So we are using the module C and module B. So the ADC resolution stands for, after you convert, analog value has infinite precision. So for a digital system, we are converting to digital. There are only finite bits. So the C2000 support 12-bit and 16-bit. So we are using 12-bit. So this analog value can range from 0 to 4096 values. And SOC stands for start of conversion, and SOC accusation window, which means how long the window is open to. Inside this ADC module, there is a sample and hold circuit which will sample and it will hold that value. So that sampling window, so that window, how long that gate is closed to allow the inner capacitor in the sample and hold circuit to be charged, so that window is 15. So if you make it longer, it will be more accurate. This we have chosen to be 15. And SOC trigger source, the start of conversion is triggered by the EPWM module. So this is configured by us. So ADC EPWM SOCA. So this module will trigger the start of conversion for this ADC. And sample time -1 means it is inherited. So our system's sample time is inherited. So you can see in the name TS. So our TS is, I think, 20 kilohertz, 25 kilohertz, I think. So our PWM frequency will be our TS. And the data type this block will output is unsigned int U int16 and post interrupt at EOC trigger. That means post interrupt at end of conversion. So after the value has been converted, it will post another interrupt. So that interrupt is being named as ADC int1. So that's all the configuration of this ADC. So when you are in the hardware generation mode, we don't need the simulation currents. So this is a virtual block which we only run in the virtual simulation mode. So we don't need that when generating code for hardware. That's why we are terminating this simulation data values by using a block called terminator. So in the simulation mode, if you see that current, we directly forward that current. We don't need any processing. So that is what we are doing. So now we get the current either through actual hardware ADC or through the virtual Simulink model, virtual induction motor model. So either way we get the current. We get two currents, IA, and we are muxing the two currents inside to IA and IB, and here we are demuxing it through IA ADC and IB ADC. So we are receiving it from that. And this also, so inside this block, we are going to do processing on the current we just received. We are going to subtract with offset and the mainly we are doing the position and speed estimation inside this block. So you can see this VI feedback. So VI stands for voltage and current feedback. So it is coming from this control system, which we will take a look in the next video. So if I go into that, you can see the measured currents which we measured from the ADC is transformed to alpha beta frame by using Clark transform block. Then we are using that, we are taking that value and giving it. So this block, which means we are connecting essentially this point to this point and this beta current to this point. We are taking two currents, I alpha, I beta, so which are the transformed versions of IA and IB, which is in the stator frame. We are converting it to alpha beta frame. So alpha beta frame is nothing but this is our three-phase stator frame. If you are converting into alpha beta frame, there is two orthogonal vectors rotating, two orthogonal phasors rotating. So this is the alpha beta frame currents. This is how it will look like. Okay, so we are taking the two currents and two voltages. These two voltages, okay, these two voltages, V alpha, V beta and I alpha, I beta. So this V alpha, V beta is being generated into the inside this current controller. There is a PI controller which take the ID and IQ reference current generated by the speed control system, and it will compare against the actual ID and IQ current. So actual ID and IQ current is Park transformed version or DQ transformed version of the I alpha, I beta current. So it will generate a error signal. It will be multiplied with the PI gains and other things there inside, which we'll take a look at later. So that will give the VD and the VQ reference. It is in the DQ frame. These two voltages are in the DQ frame, which we give it to the inverse Park transform block, which will give the V alpha and V beta. So these are the reference voltage which we will feed into this SVPWM block. So it will give three-phase voltage duty cycles, so which will be applied to the inverter. So this V alpha V beta will be essentially applied to the inverter. So we are assuming that it will be applied, then so we are taking that terminal voltages V alpha and V beta and I alpha I beta in the alpha beta reference frame. So we are giving that. So you can see all this are going through port 2. So in the port 2, we are giving it to a flag and we are connecting to the input scaling block. So we are adding this Z power minus 1 or unit delay, because the computer, if you don't add this block, it will create an algebraic loop. So an algebraic loop is nothing but in computer, in real life, for example, from a sensor to some sensing equipment, there is a propagation delay in the wires. There is a sensor's inherent delay. So everything is there in the real world, but in the simulation, all these are virtual mathematical things. In this entire MATLAB model, if we connect two things without a delay, it will mean the computer will not understand whether the signal is starting here or here. It will create a circular reference. It is paradoxical and impossible to solve for a computer. So we have to add a unit delay, which means it clearly says to the computer the signal is starting here and propagating in this direction. It gives the clear direction whether the signal is propagating from this side to this side. So that is why we are adding this delay. Without this delay, it will create something called as algebraic loop, which will the simulation won't be able to solve. The numerical solution will not be able to converge to a particular value. So that is why we are adding this delay. So the voltages and currents, two voltages V alpha V beta and two currents I alpha I beta are coming here. So let's first look at the IADC. So our from our hardware or from the virtual motors terminal, we are getting this IAB and IA and IB. So inside this, we are subtracting the offset. So this IA IB is an offset value. So we are subtracting that, and so from this we are converting. So this the data type of this is integer 16-bit integer. So we are converting it to int 32. Then we are subtracting the offset. So I will show you on graph. So this is our current waveform. So actually we want to, since it is an alternating current, if you give the directly to the ADC of this, what will happen is the negative half cycle will be cut. So the digital system will work in the 0 to 5 logic level or 0 to 3.3 logic level. So if the voltages go below this, it will be clipped or it will be cut off. So the waveform will be distorted. So we cannot able to read it faithfully. So what we will do is we add in our sensing circuit, there is an op amp. So we will add a bias voltage to that. So which will shift the entire waveform. So our ADC, our ADC is a 12-bit ADC, so we have a resolution between 0 to 4096 or 0 to 4095. So our ADC is 12-bit ADC, 2 power 12 is 4096. So 0 to 4095 we have this range. So if you don't add this bias, the negative will be clipped. So only the positive half cycle will be coming to the microcontroller. So what we will do is we'll add a bias in the voltage bias in the op amp. So then the entire waveform will be shifted. So this is our current, this is our motor current, which will be scaled appropriately. So for example, if the motor current is 2 amps, there will be shunt resistor connector across the motor terminal, which will give a proportional voltage according to the resistor we put on that shunt resistor. So that proportional voltage will that voltage will vary in proportional to the current flowing into the terminals. So we will scale it appropriately to make sure we don't damage the ADC of the input port of the C2000. So then this wave will look like this. So we are shifting because we want the faithful reproduction of the motor's AC wave. So we have to subtract the shift after we measure. After we get the values inside the C2000, we have to subtract this offset. So for example, normally we shift the wave to the half of the ADC resolution. So for example, 4000, let's assume the ADC resolution, we will shift 2000. So our 0 is 2000. So plus 2000 is the positive half cycle, and below 2000 it is the negative half cycle. So we have to our zero. So now our level 2000 is our 0 level. So we have to subtract that 2000. So that is what we are doing with this I and IB offset. We are subtracting essentially the offsetted value. Our bias voltage we are subtracting. So then after we subtracting, this is a data type conversion in which our subtracted value gets multiplied with the target. Target is nothing but our C2000 or the deployed hardware. So our processor is our target. So this target.adc vref is a variable which I will show where to look for. So if you right click on, okay, if you double tap on this mcb foc data.m, you can see this is the target equal to mcb processor details. So this is a function. We will pass the target hard, this is our launchpad's number. You can right click on that, then select open mcb process detail. Let's open this script. So this script is nothing but a function. So since our board is F23879D, or you can see they have just hard coded all the values here. So you can see the target.adc vref is 3 volt. So our microprocessor works in the 3 volt logic level. So that is what we are doing here. So target by ADC max count. So since our ADC max count is 12 bit, so we have 4095 for 12 bit ADC. So this is essentially we are okay. So target ADC, let's do the calculation. So 3 by ADC max count is 4095. So this is the value 0.00074 something. So when we multiply this fraction, this value with our actual measured ADC value, we will get the ADC voltage. So in ADC we are getting the values from 0 to 4095, right? So we want to get the ADC voltage. From that voltage we are going to get the current. So let's open here. So we get the ADC voltage by multiplying with this fraction. So after that we have another fraction which is 1 by inverter dot I sense volt per amp. So current sense volt per amp. So this is also a number which we can see here. If you open the data file, there is an inverter. You can right click on this. Make sure your cursor is on this particular function. You can right click on this, open set inverter parameters. So you can see, so if you are using any of these inverters, this is the voltage per ampere. So if you have any other inverter, you have to set it manually. So our I sense volt per amp is 0.1. So that means if our motor has 1 amps of current flowing into the terminals, we will get 0.1 volt. This amount of voltage is determined, as they say here, by the shunt resistor and the I sense, the current sense op amp gain. So with these two, this value is decided. So when we multiply the voltage, the ADC voltage with this fraction, we get how much of motor current is flowing into the terminal. Then it is a simple per unit conversion. Per unit means actual value by base value. So the our motor and inverter, so we choose one base value, base current. So we will divide it by that current. So I base. So PU system dot I base. So our system base current. Then we get the current. Then it is for inverting the sign. So if you are measuring the current direction, which is determined by the op amp, if it is inverting or non-inverting amplifier, so it is 1 or -1. So now we have taken the two ADC currents and we have converted from an ADC count value, so 0 to 4096, to the actual current in per unit. So that is about the current measurement block. So now let's go into the speed estimation and position estimation block. This is the heart of the sensorless scheme. So we are estimating the currents and voltages. We are estimating the position and speed based on the current and voltages. If you double click on that, you can see the input signal, which is our V alpha V beta I alpha I beta, is going through a high pass filter. So this is high pass filter operation, means it will remove the low frequency noise. So the not noise necessarily, low frequency component. Low frequency component is nothing but a DC component. So this, since I alpha I beta are in the alpha beta reference frame, these are the oscillating currents. As we saw, it is like an AC wave, but only two components are there. So this AC component should not have any DC in them. So we remove that using this infinite impulse response or IAR filter. This gain is calculated in our script if you want to take a look. So all the four signal is demuxed. So all the four signal is demuxed and given to this flux observer block. This is an inbuilt block. So which take all this. If you double click on that, you can see. So it computes the electrical position of the rotor, which is the angular position, and the rotor magnetic flux, which we don't need. This block can calculate position of the rotor flux, rotor flux, and the electromechanical torque. So we only use the position of the rotor. So we use the position to estimate the speed. So this block can estimate the position and flux and torque of PMSM or AC induction motor. ACIM stands for AC induction motor. So we are using AC induction motor, and the input is in per unit, which we are using. So we have converted all the values in our FOC system to per unit. So we have given the base voltages and base current to this block. And so to estimate the rotor flux, it needs all these parameters. road resistance, stator leakage inductance, rotor leakage inductance, magnetizing inductance. So all these parameters are we need to measure. So it will be not most of the data sheets won't mention these. We have to conduct test and measure this. So that is the drawback of this sensorless scheme. So we have to measure that. Then internally there is one filter. So that filters cutoff frequency. We can give the cutoff frequency, so we can specify the cutoff frequency for that here. Okay, so TS is our sampling time. Okay, we will take a look at the equations. So this is the flux observer block. So you can go and search for flux observer MATLAB, then you get the documentation. Or for example, if you right click on that and help, if you press on the help, it will open the documentation of the flux observer, where you can see all these equations for PMSM, all these equations, but for induction motor here it is. So these are the equation. I took the equations from here. So V alpha, V beta, I alpha, I beta are the things we are giving. R is this stator resistance. All these are we are giving that. So let's understand this equation intuitively. Okay. So okay. So we know from the Faraday's law, the EMF induced in a system is proportional to the rate of change of flux, or the flux linking through it. So if you want to get the flux, we know the EMF. Let's assume we know the EMF, then we need to calculate the flux. So what we'll do is we will integrate on both sides. So integral E is proportional to integral of d phi by dt with respect to time, which will give phi, the flux. So here they are using this symbol psi. Okay, so this E, okay, I will draw a diagram. So I will draw one phase of motor. So this, it will have some resistance, inductance. So this is the induction motor. Let's assume one phase of an induction motor. This is the terminal voltage of the induction motor, which is V. We are applying. We know this voltage because we are giving the gate pulse. We know this voltage. So with this voltage, and we know the current because we have a shunt resistor which is giving a real-time reading of the from the ADC. From the ADC we are getting the current. So I know the current, I know the resistance. So this is E, the voltage which is behind all this resistance and inductance. So we cannot measure this. If we measure, we can only measure the terminal voltages. If you measure the terminal voltages, all the coils, inductance, resistance gets effects of all that is getting added. Okay, we cannot measure this internal induced voltage. We can theoretically do this in this circuits for mathematical analysis, but practically we cannot measure this. So this internal induced machine voltage is proportional to flux. So this internal machine voltage is nothing but V minus IR. So since all the voltages are in alpha beta frame, V alpha equal to V alpha minus I alpha into R. So this R is the resistance of the motor. So this E is this. So now let's look at this equation. So we are integrating this V minus I alpha into R. So which is nothing but E. So we are integrating this induced EMF to get the flux, and all these are to calculate how much of the flux is linking with the rotor. So this, it represents the electromagnetic flux linkage, and this factor represents the amount of flux we want the rotor flux. We subtract the stator leakage flux from this, and then we also remove the rotor leakage flux. So by this fraction, then we get the rotor flux, actual rotor flux. So useful rotor flux. So then if we get these two, that is flux in alpha axis and flux in beta axis, we can use this formula which is taking the arc tangent or tan inverse of psi alpha by psi beta by psi alpha. Then we are getting the rotor's electrical position. So that is how this flux observer block works. You don't need to know this, but if you this is an inbuilt block, so you can treat it as black box. But to get a better understanding, you can see all these formulas and how it is calculating. So if you go into this by pressing Ctrl U, you cannot double tap on this like a subsystem. You have to press Ctrl and U. Essentially, they are abstracting all this from you by using a mask just for our convenience. Psi alpha, psi beta, as we saw here, the psi alpha and psi beta. If you go into, for example, psi alpha, I alpha into R, I alpha into L. So all this equation is implemented in the graphical environment. Then we are integrating the V alpha minus I R. Okay, this V alpha minus I R. Then we are integrating in this. So this is getting integrated. The previous value is getting cumulatively added. That is nothing but integration. Then so this high pass filter. So to remove any low frequency component, for that only there is a cutoff frequency. So then after this we are calculating the flux, we are calculating the position, torque. So since we have unchecked the torque and the flux, it is going into the terminator block. We are not using that, we are only using the position. So the position inside this, we saw in the formula, there is an arc tangent. This tan inverse of psi beta by psi alpha is implemented here. So arc tangent of psi beta by psi alpha. Then we are getting the position. So that is how the position of the rotor is computed. So now we know the position of the rotor, and since V alpha, V beta, I beta are instantaneous value which we keep on changing, we also know we also can infer that the theta will also be changing, the rotor position will also be changing. So if we know the position at every instant, we can calculate the speed by calculating the rotor was here at this instant and the rotor was here at this instant, how quickly. We know the time and position, so with this we can calculate the speed. That is what this speed measurement block is doing. This is also an inbuilt block. So it takes all the parameters like maximum speed, time step, and system base speed, etc. So okay, so as we know, the speed is nothing but how quickly the position is changing, or the rate of change of position. If the rate of change, the theta is changing quickly with respect to time, the speed is also high. So inside the speed measurement block, if you press Ctrl and U, you can go into that and see. So all this is for data type conversion. The main core aspect of this is here. So what we are essentially doing is rotor at 1 second. Okay, at 0 second the rotor is at 0 degree, and at 1 second, 1 second of time, 1 second has been elapsed, then the rotor is moved 50 degrees. So the rotor has been moved 50 degree per second. So this is nothing but speed, angular speed. So that is what this block is doing. So what we did is 50 minus 0. That is what we did, right? 50 minus 0. For example, in 1 second the rotor is at 50 degree, and the second the rotor is at 60 degree. So what we do is, how quickly this has changed is 60 minus 50 degree in 1 second. So 10 degree per second. So this is how we calculate the speed. So we are subtracting the latest speed, the current speed, the previous speed. So that is what is happening here. So that is how the speed measurement block works. Now the speed should not have any high frequency component. so the speed should not change erratically. So we are adding a low pass filter which will remove any high frequency component. So then we are getting the slip speed from a slip speed estimator block. This slip speed estimator takes all other induction motor parameters and currents to calculate the slip speed. The slip speed is nothing but the synchronous speed minus the actual rotor speed. So we don't know the actual rotor speed, that is our aim. So we don't connect any sensors to the rotor shaft. So we are estimating the speed based on the rotor's currents and voltages. So let's see. So let's assume that our synchronous speed is 1500 rpm for a 2-pole or 4-pole machine. So for example, assume this is 1500 rpm and our rotor speed is 1400, which we don't know yet. Which we don't know, but let's assume I know this. So the slip speed is 1500 minus 1400, so which is equal to 100 rpm. So this is our slip speed. So we use a slip speed estimator to calculate the slip speed. Then we subtract, you can see here, we subtract the actual synchronous, this this flux speed is nothing but our synchronous speed. So the rotor flux and the stator flux commonly refers to as mutual flux in the machine rotates at the same synchronous speed. We are essentially taking the synchronous speed and we are subtracting it from the slip speed, which is 100 rpm for example. So this is 1500, this is 100 rpm, then 1500 minus 100 we get 1400 rpm. So that is essentially how we are calculating the speed of the rotor, which we are estimating from all this. So this is also coming from an estimator, this is also coming from an estimator. So that is why it is called a sensorless scheme. Then all these are in electrical speed. Then we are dividing by number of poles to get the mechanical speed. So this theta is the rotor position which we are using in the current control system for the DQO transformation. So from the alpha beta frame, if you want to go to the DQO frame, you need theta. It requires sin theta and cos theta. For the theta, we are taking the theta from the flux observer block. So that is where this theta is going. So it is going into the port 1, two things. And let's come back and this position and speed. So this position, so our motor initially will run in the open loop mode, then it will transition to closed loop mode. At approximately 20% of the rated speed, it will transfer to the closed loop mode. So until after it has been transferred to the closed loop mode, then we will use the actual position computed by the flux observer, which we just saw. So we will use this theta to we will use this theta for the DQO transformation and other further processing. Until then, we will use the speed reference, which is the variable we will set from the host computer. We will use that to approximate. So speed is nothing but how quickly the position changes, right? So we are doing the inverse here. So we are given the speed reference from the host computer. We are getting the theta from that. So we are getting the position from the speed reference. So after the closed loop has been enabled by this flag, so then we will transition to the theta estimated by the flux observer. Initially, we will run in the open loop mode. For the open loop mode, this is the theta. So this theta is used by the this Park transform block, which takes so it will get the theta and it will compute sin theta and cos theta by using a lookup table, which is a bunch of values. Sin of theta, all the values have been stored in a table, predefined table. It will just look up that value and take that value, and it will transform our alpha beta values to the DQO frame. So that's all. Thank you.